All right, so last time we met, we talked about how to draw a heat diagram. So we're going to do a pretty easy one before we start, just to refresh our memory. Okay, so here we got a pizza in an oven. So let's say that we have a pizza. So I'm going to draw the oven real quick. All right, so what we're going to do is we're going to really quickly draw this scenario. So we got our, let's say this is our oven. And then let's say we got our pizza inside. Okay. And then inside the oven, there's obviously air around the pizza, right? And basically the oven, it heats up the air. Okay, now what's going to be warmer? The air around the pizza or the pizza itself? Yeah, the air, right? So obviously, since it's warmer, energy is going to go from high energy to low energy. So from the air into the pizza. And so if the pizza is the system, energy is going into the system. So what do we call that? Endo or exo? This is endo, correct. Okay, it is endo because energy is going in to the system. Yes, that's also how microwave works. All right, so today we're going to be learning about something called enthalpy. And I know we've been looking at endothermic and exothermic systems, but now we're going to talk more about chemical reactions. So I'll tell you guys what's important to write down and what's not, so you guys don't need to copy everything. Okay, but a lot of times when we have a chemical reaction, energy, thank you, is absorbed or released in the form of heat, light, and or sound. So take a second to copy that down. Okay, so the term for energy going in and out of the reaction is called enthalpy of the reaction. That's the title of the lecture. And the symbol for enthalpy is this triangle H. It's called delta H. It just shows the change in energy. Okay, and delta H is going to always equal a number. Okay, so and then we're going to measure that in terms of either joules or kilojoules. So there's going to be a number, and then we're going to write kilojoules behind it usually for this class. Okay. So that's just telling you how much energy is going into the system or coming out of the system. 6. So again, energy is absorbed or released. We call that the enthalpy of the reaction. And the symbol for that is delta H. And it's going to be a number and then kJ or kilojoules behind it. So like we learned last time, there are two types of reactions, right? There are exothermic reactions, and that's when energy goes out of the reaction. Okay, and when you have an exothermic reaction, the delta H is a negative number. So a good example of that would be something like an explosion, right? Heat, light, and sound come out of a chemical reaction that produces an explosion. That's an exothermic reaction. So the number for delta H is going to be a negative number. So let's just say something like negative 100 kJ. So you'll have a negative number or a negative sign and then a number behind it. Okay, and the other type of reaction we talked about are endothermic reactions. That's where delta H is positive. Okay, and so you'll have delta H and then you'll have a positive number. Just keep it simple, like 100 kJ. Okay, so by looking at the delta H, you guys can tell really quickly if something is exothermic or endothermic. Basically, is energy going to come out of the system or is energy going to go into the system? Okay, so that's enthalpy. That's pretty much all the new info for today. All we're going to do now is do some stoichiometry with this now. Okay, so what we're going to do now is we're going to combine this with stoichiometry. So don't feel pressure to copy everything right now. I'll tell you guys what order to take it. But before we start, don't copy this down yet. I want you to just look at the reaction, okay? So the reaction is basically telling us we are combining aluminum and we're combining that with HCl. So that's actually the reaction we're going to run up here in a second. And we can answer the first part of the question just without doing any math. Will energy be absorbed or released? So we're going to look at the delta H. If it's a negative number, is energy going to be released or absorbed? Yeah, it's going to be released. Okay, so for part A, the answer is released. And we know that it is an exothermic reaction, and that's because the delta H is a negative number. So make sure you guys jot that down. Okay, in this reaction, if you mix aluminum with HCl, it's a type of acid, energy is going to be released. So we're going to do that up here right now as you guys work on the problem. And so I'm going to let you guys touch the reaction once it starts, but you should expect energy to be coming out of the reaction. Okay, so take a second to copy down the answer to number or part A. And then after that, if you feel comfortable, start balancing this equation right here. Okay, so copy down part A and balance the equation. I'll start setting up the reaction right now for you guys. All right, so for your counts, should be pretty simple. You got one of everything on the left side, and then you got one aluminum, you got 2 hydrogens, and 3 chlorines, okay? All right, what we want to do now is we want to make sure they're balanced on both sides. Now, if you notice, we're going to run into a problem because we need to balance the hydrogen and chlorine. So we're going to add HCl. But if we add 2 more HCl's, that gets us to 3 and 3. So chlorine is balanced, but hydrogen is not balanced, right? So we're going to have to go to the other side and add hydrogen. But if we do that, you're going to notice we have 4. So we got to add hydrogen again to the other side. So we add another hydrogen, but that gets us to 4 and 4. And unfortunately, that means we have to add AlCl3. Okay, which brings our aluminum to 2 and our chlorine to 6. And that's how we can finish up this problem by adding 2 more HCl's for a total of 6 and another H2. Okay, so that gets us a 6 and 6 here. So your coefficients will be, oh, and you got to add another Al. 2, 6, 2, and 3. Okay, so if you guys got that on your own, great job. I won't give you anything harder than that for the balancing. That's pretty much it. Okay, but now that I know you guys use the app, which I've known, the people who admitted to using the app all the time.
What app?
I don't really care.
The app?
There is an app that balances for you. Or a website too. So for the actual part B, we are looking for how much energy will be absorbed or released. So in this problem, we are going to be starting the same way we start a regular stoichiometry problem. If you guys notice, the starting number is 2 grams of aluminum. So our starting number is 2 grams of Al. Okay? The problem is asking how much energy will be absorbed or released. So at the end of this problem, we are looking for energy, and the way that we measure energy is in kJ. So we're going to write kilojoules. So that's our starting or ending. And now we just need to set up our fractions, and then we'll be all done. Okay?
Oh my gosh. Wow, look at that. Oh.
All right. So let's set up our reaction. So for our equation, our starting number is 2 grams of Al. So same thing as regular stoichiometry. We're going to write 2 grams of Al. Okay. And this new type of stoichiometry is a lot easier than the regular one because instead of 3, we just need 2 fractions. Okay, so 1 less fraction than before. All right, let's set up the first fraction. The first fraction is the exact same thing as regular stoich. On the bottom, we're going to put grams, and on the top, we're going to put moles. And it's going to be about your starting chemical, which is Al. So we're going to put Al on the top and bottom, and we're going to get the numbers from the same place as before. We're going to get the numbers from the molar mass. So I want you guys to take out your periodic tables, and I want you guys to see if you guys can write down the molar mass of Al on this fraction. Okay, so take a second to do that, and then we'll double check in 1 minute. So if we pull out our periodic table, you guys will see that Al has a molar mass of 26.98. So on our fraction, we're going to write down 26.98. But if you guys remember, the units of measurement are grams per mole. So 26.98 goes on the bottom next to grams, and 1 goes on the top. Okay, and we're halfway done. Okay, the second fraction is also similar to regular stoich. You're going to get the numbers from the balanced equation. Okay, so on the bottom, we're going to put moles of Al. But since we want to end up with Kj, we're going to put Kj on the top. Okay, so for the number on the bottom, we're looking for moles of Al. So we just look for the number in front of Al, which is 2. And then on the top, we're going to put the number that we have for Kj, which is the delta H. And it's going to be negative 502 on the top. Okay, so that's how we plug in all of our numbers for this stoichiometry. All right, so I'm going to leave that up there. I'll give you guys about a minute. See if you guys can punch that into your calculator and get your final answer. But as you guys are doing that, I'm going to walk around with the reaction that we ran. We said earlier that it's exothermic, right? So energy is released. So when you touch it, you'll be able to see that energy was released from this reaction. So I'll be walking around, but while I do, finish up this problem and see if you can get the final answer. All right, let's see if you guys got the math. So the rules are the same as regular Stoich. You multiply the top, divide the bottom. So your starting number is 2. There's 26.98 on the bottom. So you're going to divide by 26.98. You're going to multiply that by 502. And then you're going to divide that by 2. And it's a negative number. So your final answer will be negative 18.6 kilojoules. Okay. So again, I'll write down how we got this number. It's regular Stoich or regular math. It's 2 divided by 26.98 times negative 502 divided by 2. Okay, so I want you guys to try this one. It's very similar to what we just did. You're looking, is it exo or endo? And then you're solving for how much energy is released or absorbed. And then after we go over this together, I will show you what the reaction looks like, and then we'll be all done, okay? All right, so let's start with if this is exo or endo. Is this an exo or endothermic reaction? Yeah, this is exo because the enthalpy is negative. So energy will be released. So in a couple minutes, when we run the reaction, you guys should see energy being released from the reaction, okay? All right. Our starting number is 0.22 grams of H2. So we're going to write down 0.22 grams of H2. And then we're going to set up 2 fractions. All right, for the first fraction, we're going to get the numbers from the molar mass of H2. Now, H is 1.01. So if there's 2 of them, it'll be 2.02 grams of H2 in every 1 mole. For the second fraction on the bottom, we're going to put the moles of H2. And if you notice, there's a 2 in the front. So we divide by 2. And then for our delta H, our energy, it'll be negative 570 kilojoules. And there you go. That is going to be your setup. Any questions on the setup or the fractions? If you got 2, that's fine. Yeah. This one is close enough to round down. Okay, so let's plug and chug into the calculator. So our starting number is 0.22 divided by 2.02 times 570 divided by 2. And so our final answer will be negative 31, and I'm going to round it to 0.4 kJ. And that's it. Kilojoules. 31 kilojoules in this reaction. All right, so let's run this reaction now. I'm going to take our balloon of H2, and I've already done the math. We created about 0.22 grams of H2. And so I'm going to show you guys now what it looks like when 31 kilojoules are released in this reaction. Okay.